I'm Timothy Williams from the NERSC Centre in Bergen, Norway, and presenting some work with my colleagues Pierre Rampal and Syvain, Bouillon and Abdoulaye SamakeThe from the NERSC Centre as well, who are developers of the neXtSIM CIS model, which I'll be using, which I'll be presenting wave results when they're coupled to this model. So, the outline of the talk, I'll just give a bit of an overview of the CIS model itself, and then some some information about the coupling and also the wave ice module, the WIM for short, and another option for coupling to the neXtSIM, and a few results and some future work and conclusions. So there's different aspects of wave ice interactions, not all of them included in the current results, but wave attenuation is there. Thermodynamics not included so far, but they are known to be it's known to have some effect, like the heat fluxes between the gaps between the ice flows, and there's increased lateral ice melting and freezing due to the breakup of the ice. There's dynamic effects once the ice is broken up as well. It becomes more of a granular material. It's still unknown how to model this exactly. Inside the neXtSIM framework, which uses the elasto-brittle rheology, there's a couple of parameters you could try to change, which is the damage parameter and the cohesion and the material cohesion parameter. There's other theories being proposed, which the group at NOC Southampton have been implementing in SICE and NEMO, this collisional rheology of Denny Feltham, which is a modified VP with a temperature equation coupled to that. Yeah, another related property is the ice edge location, and it's quite important for things like currents and winds, and it will also affect the thermodynamics and the dynamics, and more directly from the waves, the attenuation provides some momentum. As the waves are attenuated, as the waves travel into the ice, they are attenuated and lose momentum to the ice and the ocean and the atmosphere. So we have used the neXtSIM CIS model to test the impact of waves on the ice edge in a fairly simple experiment, or experimental domain is fairly idealized. So a bit of information about neXtSIM itself. It's a Lagrangian CIS model on a finite element mesh. The rheology itself is probably the most validated, particularly the spatio-temporal scaling of the CIS deformation. What I mean by that is that as you change the length scale over which you average the deformation, or the time scale over which you average, then you sort of tend to get a power law distribution in both of these averages, and particularly to this, power laws are heavy tails where there's more extreme values, which is what's observed in the observations of CIS deformation. And other characteristics are there's strong spatial localization, which you can see in this picture of the shear rate here. So these long linear features where the shear is localized on, and also in time there's strong intermittency in time, and the drift is agreeing quite well with observations as well. and ice area NEXtSIM. So a full implementation is continuing. We're trying to have it parallelized, but this is nearly finished. And then the wave module is also being put into the main model. That also needs parallelization, especially to make it more efficient. Yeah, excuse me. So the main equations is the momentum equation, and then conservation of area, ice volume, and there's a new variable called the damage, which also evolves. It has changed according to the Moore-Coulomb fracture criterion. So when the stress reaches this failure criterion, then the damage is increased. It's also a thermodynamic healing of this damage, and this is the main variable which produces the localization of the deformations, and the reason that the Lagrangian reference frame was chosen was that it reduced the diffusion compared to a Eulerian framework. The current approach we take is the ALE approach, which is Arbitrary Lagrangian Eulerian, which instead of moving at the true sea ice velocity, it moves at a smooth version, which means the mesh gets less deformed, which means less remeshing, which is the most costly part of the model, since it's not parallelized yet. And when you add the waves, there's extra. Yeah. When you add the waves, you have an extra variable, the flow size, and this is also vectored, advected. There should potentially be thermodynamical effects due to this, but these are not implemented yet. And it's changed by the waves as the waves go into the ice. And there's also the wave propagation and attenuation included in the momentum flux to the ice. It's potentially going to the ocean or the air, but we've just put all of it into the ice for the moment, since we have just a standalone model and it's not coupled to an ocean or atmospheric model. And different time steps, we've got a time step for the wave, which is smaller than the sea ice in general, since the waves are going much faster than the ice. And there's a time step for the ice, which we use for the dynamics and the thermodynamics. And then there's a coupling, so every now and again, like half hour or hour or something, we exchange information. So there's a lot of interpolation between the mesh and the grid, which can lead to numerical diffusion if you're not careful. Okay, so just the equations for the elasto-brittle rheology. So we have, here's the usual sea ice momentum equation, and we solve it with by linearizing using the previous time step, each time step, and then there's the main, so the terms in this. So we've got this is the internal stress, the sigma, and we have a pressure term which was added to provide resistance to compaction when the ice was damaged, and it is only active under convergent conditions. And there's also the wind stress and the water stress and the atmospheric stress and Coriolis and sea surface slope. And we'll also add some terms to these surface stresses, the wave momentum flux, and there's also basal stress implemented as well. For the stress, there's it's a linear constitutive relationship. So this is a linear thin elastic plate, and the non-linearity in this part becomes from this S sigma, which moves the stress back onto the failure envelope once the sea ice is damaged. If the stresses go outside the failure envelope, then you move it back. So in this version of the rheology, the stress is mostly staying on the yield curve, so it's kind of a plastic behaviour, and this is being updated at the moment to become more brittle. So here is an example of a more Coulomb failure envelope. It's mostly triangular shaped, and we have a cutoff on the normal stress here at instead of going right to a point, it cuts off here, and depending on the scale that you're looking at, depending on the defect size, the size of this triangle becomes bigger or smaller, and this red line here is just showing the stress from a plane wave. So when it hits this, that's for later on. And just the updates to the. Whoops, I skipped a slide. Okay, I've just gone straight to some results. Yep. So this is just an example to showing the damage parameter. It's just a constant wind blowing from the left of 15 meters per second. So the wind stress is roughly 2 pascals all over the ice cover. I'll try and get that GIF to play again. No, it's not playing. Oh, here. Yeah, so it's the concentration is 70% here in this example, so it's quite loose. That was to exaggerate the movement a bit, but in this example, the ice edge moves about 100 kilometres over 2 days. So it's and that'll give a sort of a reference point for when we add the waves. And the damage, as the waves come in, the damage starts at the sides and at the corners and grows out in these kind of sort of branch-like patterns. And then I don't use this model for these results, but this is the new rheology that's being tested at the moment, which removes this pressure term, and instead in the stress equation it adds a relaxation term. So so instead of going back onto the failure envelope, the stress relaxes to 0. So it's more, once the ice is damaged, it's more it's brittle and more brittle instead of plastic. Okay, so moving on to the waves model. So we start with energy flux equation. This represents the wind input. This is a nonlinear term, and we ignore these terms for the moment, and we just concentrate on the S ice term, which is the term which provides attenuation as the waves go into the ice. So this is what this S ice term looks like in general, where the K is the scattering kernel that changes the directional distribution of energy, and alpha dissipates energy without conserving energy. So now trials of this directional scattering we found some quite unexpected results, that the waves were being attenuated as they travelled into the ice, but were actually growing to a kind of a plateau as you went further into the ice. So that's a big problem for this directional scattering theory, and it originates from the problem of converting a phase-resolving wave model, which is what these multiple scattering models do when they're deriving their attenuation from scattering. And this energy equation is a phase average model, so it's hard to include the multiple scattering properly. So for that reason, we removed this K integral and just have exponential attenuation in the direction of travel of the wave. And the alpha scat looks like this, where this is attenuation per flow, which is based on on this equation where R is the reflection coefficient for a semi-infinite plate, and that's from Bennett's Squire, which used a long flow or random phase averaging technique. That's what I've plotted here. The blue line is the result of that for some parameters like 50% concentration, 1 meter thickness, and 50 meter flow size, just setting it all constant. This is what the attenuation curve looks like. It's dropping as you increase the period. This dashed line is the fit from the Malin Beilinson Kahoot paper that Mike was referring to in his talk. This is just one choice of parameters, but it looks like it's not. It was also, when you compared to another older data set, it was also seemed like there was not enough attenuation for longer periods, which led to adding extra dissipation terms. And the one I mainly use is Robinson and Palmer, 1990. So I've also coded an approximation to the viscoelastic model of Wang and Shen, and that was using the thin elastic approximation that Musigedel presented. So the rigidity becomes imaginary, and also this term here has also got an imaginary part which contributes to damping. And then in the code I have a sort of a expansion for small values of these parameters. And then when you want to consider the momentum flux to the ice, we end up with an integral of the source term divided by the phase velocity, and this is the direction of the wave number vector, and then this becomes the stress going to the ice, the ocean, and the air all together. It's hard to know how to partition this, but for the moment and simplicity, we just have it going to the ice. And for the breakup, we just have a simple one-dimensional model. We have a plane, assume a plane wave, and assume the strain is proportional to the curvature, and that's proportional to the amplitude. And then you add a general wave spectrum that becomes integrals over the frequency and direction, and then you get a mean wave frequency, which becomes a wavelength, and then choose the flow size according to half the half the wavelength. So if it breaks, so yeah, there's been a bit of, so this is quite unproven, this breaking model yet. There's been there's a wave tank experiment last year and another one next year, which might help give some insights on the breaking process, and other approaches with the approach of Agnieszka Hermann and the discrete element approach, and that was giving slightly different values for the flow. It was becoming independent of the wavelength, it seemed, and more of the thickness. So the jury is still out on the breaking model, that's for sure. Okay, so now we've come to some results. So this is the most basic coupling option I had, which is where you take in the concentration, thickness, flow size, and incident waves, interpolate the ice stuff from the mesh to the grid where the waves are run, and then do wave propagation and attenuation on the grid, break up on the grid, and then when the call to the wave ice module is complete, then we interpolate back from the grid to the mesh, get the stresses back interpolated to the mesh, and then we also have some diagnostic stuff which stays on the grid. So here's this initial version. So go back and start the movie again. Oh, maybe I can do it here. So here's the waves coming in from the left and pushing the ice about 20 kilometres over the two-day period. And you can see the strong attenuation as the waves go into the ice. And down below there's the flow size. So as the waves come in, they where have I got to? Oh, I could use that. This is the same movie actually. So as the waves come in, the ice is broken, but there's a strong diffusion at the pack and MIS boundary. So here is an improved version which reduces that diffusion quite a lot. And the waves that improved it in that case was doing the breakup on the grid on the mesh as well as the grid. So interpolate some wave quantities onto the mesh which are much smoother, and then the breakup criterion is applied on the mesh as well as on the grid. So that means the flow size isn't interpolated back onto the mesh each call to the wave module, so it's reduced the diffusion quite a lot. So that second coupling option is relatively costly in that every wave time step there's some interpolation done, so could be tricky in general to implement it using a general model coupling tool, for example Oasis or something, if we wanted to have a full wave model coupled to neXtSIM. So I haven't got the results in this picture, but have managed to get some improvement in this option, which is more of a standard option. So in that option I interpolated the concentration to the grid and then back to the mesh as well, and then used the errors in that to try and correct this result here. So it gave some improvement. So it's this naive approach is not totally hopeless. So there may be things you can do which should also make it easier to couple in general to something like WaveWatch 3 or something. Now to come to, when you compare the wind stress against the wave radiation stress, there's a big difference in the movement of the ice edge. So the wind is pushing about 100 or so kilometres compared to just 24 or so kilometres when the wind is removed. And taking away the waves from the top experiment makes relatively little difference. So here are some plots of the axis isn't showing. The scale is about 40 kilometres altogether, and these are different parameters of the ice compaction constant and the cohesion. So these two have the same cohesion, so that wasn't making too much of a difference for the waves experiment without wind. And there's more the compaction which determines the concentration response to the response of the elasticity to the concentration. And this plot here is when there is the blue curve is so start with no waves, that's just the wind, and then there is maybe 4 kilometres or 0 kilometres difference between this red curve and the black curve, which is when you add the waves. And the blue curve is when you add the waves, and also when the flow size drops, then we also increase the damage in that area, and that gives a little bit of extra movement to the ice edge, but still relatively negligible compared to the wind effect. So main conclusions about these experiments is the wind stress dominates the wave radiation stress. The wave radiation stress can be quite high, sort of even a Pascal or so, but it's highly localized near the ice edge compared to the wind, which is over the full ice cover. There's less drift. There's not so much drift from the wave stress, but it still could be interesting from an ocean point of view if the once the models are coupled to an ocean. There could be this high wave stress could do something there if some of the momentum goes into the ocean just near the ice edge. But need a coupled model to test that properly. And the future work try and fix this diffusion issue in a way that is compatible with a generic coupler. For the wind module, it's quite costly, so we need to parallelize it. And the initial strategy is to run it on the neXtSIM mesh, which already has a parallelization implemented, but needs a bit more testing. But the main observation is that to run on the triangular mesh, you need to decrease the time step by a factor of 10, which is quite a lot. Maybe it can be improved with a better advection scheme, but still needs more work on that. And finally, acknowledgements to our supporters, the Research Council of Norway, European Commission, and ONR as well. Thank you very much.
Thank you, Tim. Questions?
When you did those simulations, did you have to randomize your field so that you initiate your damage, or whatever?
No, we just started from just zero damage, and so it could be different with the
because it looks like the propagation is not uniform front, even though, if I assume everything was uniform initially.
Yeah.
How did it happen that you have those jagged front.
Yeah, you just get sort of a cascade of if you get a strong stress, like in those corners where it's strong compression, then one cell gets damaged, and then you kind of get a cascade of damaging along these thin lines. So that's what was happening here.
On that point, Tim, the damage is updated on every time step. Is that right?
That's right. Yeah.
Okay. So those features you saw at the edge, I mean, one would imagine in reality are due to elastic propagation of stress, giving those failure lines over large distances. But in practice, the speed at which they can transfer is determined by the time step, because you're updating the damage every time step.
Yeah. Yeah.
So a bigger time step might mean a faster evolution of those features.
Yeah. It's I think the elastic waves are too fast to capture. So yeah, but we just assume that they are kind of infinitely fast in a way. And but that's the damage evolution is a tricky thing. Yeah.
Hey Tim, thanks a lot for this talk, and I think it's really interesting what you're doing. I feel like I could discuss this for you for hours, but a couple of things, like, can you just show that figure of the comparison with data and with your model, with the scattering model?
Yeah. I'll just try and find it. Next page up. Oh, okay.
You've managed to break the computer, Tim, which is an achievement.
Yeah. I don't know, where's the slideshow here? It is.
That?
No, you can't see it.
He hasn't broken it.
Yeah,
I mean,
it's not really a comparison, but
what's that?
it's not really in comparison, just to draw them on the same.
But I think that says to me that scattering is wrong. It doesn't tell me that scattering's wrong at long periods, does it? Because those are just two curves crossing. I mean, right?
Yeah.
I mean, two curves that have different slopes will cross at some point. I think there's some theory about that. Yeah. So that's interesting in itself. But what I was thinking is, there's a strong, what's the dependence on thickness in that simple scattering model you've got? Does it go as thickness squared, thickness cubed? Do you know that?
Yeah, I never really looked at the scaling of it, no. Yeah, it's just...
Okay. Because that would be an interesting question, because it's another thing that we could try and observe in the data.
Yeah.
Because it does, because the toughness goes as the Q. Yeah. The other thing is, I don't understand why you felt like that something's wrong with that result, with that saturation and the rising, because I never saw that.
Yeah,
With the one with that...
you never saw this?
With that scattering, when you include the scattering.
Yeah, that's... we tested that quite fully, and it seemed to be a real thing. But
certainly, I'll look into that. Yeah.
Yeah.
See it.
So I've never seen the actual total energy in any of the scattering papers. They always concentrate on the directional distribution relative to each other. But the multiple scattering models all have localization at the ice edge where it's decaying exponentially. So it's
There is a way to, Haley's student published a paper, or Haley and her student, I should say, on this way of going from the diffusion model, like Einstein did, with his Brownian motion, to compute the, to take the limit properly rather than just this ad hoc method.
okay.
To go from the phase resolve to the energy.
Okay.
Haley, did you? Yeah, nodding.
Yeah.
Actually, it was because of Eric Rogers' comment several years ago. He said, scattering is really a diffusion process. So we looked into that and found those bio-optic people, they have done that. So we use the
Yeah.
But localization is the absence of fusion.
Yeah, local. No, we didn't.
Yeah, but it's another whole. It's a massive project to start now. It's not going to give the answer straight away, but it's a part. I think. Yeah.
You may
It's not localized though, because the energy was localized. Then, if you imagine the way the energy is in some space in the marginalized zone, it's localized. It can't get out, so it'll all be stuck there forever. And that's not what we. I don't think there is localization of energy in the marginalized zone.
That's the attenuation. That's
Yeah.
the energy is more at the light edge and decays into the ice.
I think our localization model gives attenuation that doesn't match the data.
But there's no scattering in that data that's in the show. Anyway, maybe a conversation for later.
I ask a more basic question. Okay, I don't care if it's localized or scattered or whatever. I want to make sure it's conserved. And you made some comment about energy not being conserved, and that's a major no-no if you want to incorporate this into the client model. So what's going on?
It's a big theoretical problem.
It's also
Possibly
this
it
will
has
not
to
be incorporated into any client model if you're not conserving energy. So
probably it has to be reflected back somehow. It's hard to fit it into these energy propagation models. We don't really. That's another reason why you need other mechanisms for dissipation. If it was totally reflected, then it would. Then it's clearly not being totally reflected. So that's one thing. But probably the model should say that if there's no dissipation, it should all go back. But that's where the other dissipation methods come in. But
it's not being dissipated, or the wave energy should all be scattered back? External wave?
Yeah, I think so, yeah.
Okay, so it will be dissipated, so it'll go into the ocean. But
yeah, I was going to say, surely you're not requiring energy to be conserved within the ice. It could go to the ocean. Or
oh no,
it could go to
absolutely,
the
yes, yeah. I don't mind
atmosphere.
where it goes, but I would imagine it would go into the ocean. That'll be.
It has to.
Yeah.
Mm-hmm.
So the point is that if it's going to go into the ocean, it's going to enhance the mixing in the mix layer, so it's going to have an impact.
Yes.
So that needs to be accounted for. If you put in one part of the model which doesn't conserve energy,
Yep.
okay,
Yeah, sure.
no client model is going to like that.
So one more comment to that. The last, it's kind of the I forgot what I was going to say, but the alternative to have if you have the conservation of energy, then the waves go too far in, and you eventually get too much braking, for example. So this preserving the localization, I thought, was preferable to preserving the energy conservation if we didn't know how to do it properly. So.
Couldn't you just take all that energy loss and just sink it in the water's warmer? Right? I mean, it's got to go into heat eventually, right? Where's it going to go?
Well, eventually, but it might go.
Where do you think it's going to go?
The way before it gets heated, it may mix up the ocean totally off the next layer depth, and that may have a much like a 10 times bigger impact than these in the first place. So you can't just first say, oh, let's turn it to heat. That's a bit of a
I think it's going back to my comment, and it's what we've got no idea where it goes.
yeah. Okay.
Criticizing what we're doing here. Why are we going to come here and
Well, I'm just saying that making the ocean temperature increase by like 0.1 degree is not the way to solve it.
You get your energy conservation.
Oh, you can't change.
Quite a big problem.